9.3 Polarity. In Chapter 8, we discussed bond dipoles. But just because a molecule possesses polar bonds does not mean that the molecule as a whole will be polar. As in the case of carbon dioxide, we can see that there are two bond dipoles, but because they're equal in opposite direction, we do not have a polar molecule. They cancel each other out. By adding the individual bond dipoles, one can determine the overall dipole moment for the molecule. In the case of water, which is bent, we have two dipoles, indicating that oxygen is the more electronegative atom, and that the overall dipole moment, here shown as red, indicates that that's where the electron density is. Here are several examples of molecules. We can look at them individually. First, we have our HCl molecule, which is polar. It is linear, and the electrons are being pulled toward the chlorine. In the case of CCl4, even though there are four dipoles, they are all symmetrical and they cancel each other out, making the entire molecule nonpolar. In the case of BF3, which is a trigonal planar molecule, again, there are three dipoles that are very symmetrical and cancel each other out. In the case of ammonia, we have a trigonal pyramidal structure. This one is polar because of its molecular geometry. The electrons are being pulled toward the nitrogen. And finally, in the case of CH3Cl, we have the electrons being pulled toward the chlorine in this polar bond, or in this polar molecule. Sample exercise 9.4, polarity of molecules. Predict whether the following molecules are polar or nonpolar. For A, we have BrCl, B, SO2, and C, SF6. We are given the molecular formulas of several substances and asked to predict whether the molecules are polar. If the molecule contains only two atoms, it will be polar if the atoms differ in electronegativity. If the molecule contains three or more atoms, its polarity depends on both its molecular geometry and the polarity of its bonds. Thus, we must draw the Lewis structure for each molecule containing three or more atoms and determine its molecular geometry. We then use the relative electronegativities of the atoms in each bond to determine the direction of the bond dipoles. And then finally, we see if the bond dipoles cancel each other out to give a nonpolar molecule or reinforce each other to give a polar one. So for A, we have BrCl. Chlorine is more electronegative than bromine. All diatomic molecules with polar bonds are polar molecules. Consequently, BrCl will be polar, with chlorine carrying the partial negative charge. It is suggested that you reflect back on the Pauling electronegativity scale to see exactly what the numbers involved here are. The actual dipole moment of BrCl, as determined by experimental measurement, is 0.57 debye. In B, we're looking at SO2. Because oxygen is more electronegative than sulfur, SO2 has polar bonds. There's three resonance forms that are drawn below. For each of these, the VSEPR model predicts a bent geometry, just like that of water. Because the molecule is bent, the bond dipoles do not cancel each other out, and the whole molecule is polar. Experimentally, the dipole moment of SO2 is 1.63 debye. And for our last example, SF6, fluorine is more electronegative than sulfur, so the bond dipoles point toward the fluorine. The 6 SF bonds are arranged octahedrally around the central sulfur. Because of the octahedral geometry, which is very symmetrical, the bond dipoles will cancel and the molecule is nonpolar, meaning that we have a dipole moment of equal to 0. Practice exercise. Determine whether the following molecules are polar or nonpolar. NF3 and BCl3.